Hello, folks. So, welcome to part 24 of Learning Rust series. And today is day 11 as part of my 100 days of Rust. And interestingly, I was just loading this web page, Rust programming language, and I noticed that 162.1 is an older release now, and we have 163.0. And if you click on this, you will go to the blog post where they announce this new version and they talk about what's there, like what's in this. And if you go to this, GitHub, their source code, Rustlang Rust, you notice the older version. I think they would have put the newer version. No, but there is a tag for the newer version. I think they're yet to put some details around it. So just 25 minutes ago, this tag was pushed. So they'll put some details over here, I guess, soon. But the post is already out, and we can already just start using the latest version. So let me try to do this. You can say update and stable. Yep, I just did update and it just worked. You can also do this update stable. So while this goes on, I'll also check up what Rust update health shows, like toolchain, and toolchain can be stable nightly and whatnot. Okay. This is the like optional, I guess, because this stands on its own. So now I'm wondering how this is running. Like the, I mean, will it run Rust compiler and do stuff, the latest version, or what it'll do? Now the Rust team is happy to announce a new version of Rust. Okay, 1.6.3.0 programming language empowering everyone to build reliable and efficient software. Nice. The previous version can get cool. If you don't have it already, get Rust up. And then from the appropriate page on our website, check out the detailed release notes. Ooh, it looks like they have detailed release notes for every release over here. Nice. Cool. I think this must be a really big one. Yeah. Let's see. Yeah, 126. Interesting. 162 should have had one too. Yep. Cool. If you would like to help us out by testing future releases, you might consider updating locally to use the beta channel. Okay. Or the nightly channel. Please report any bugs you might come across. Okay, cool. So if you want to actually contribute to Rust, which you should, I think, if you are like already learning Rust, I think it's a great way to actually start learning some language. You can contribute to the language compiler, interpreter, whatever it is, compiler front ends and whatnot, right? So what's in 63, 163 stable scope threads? Okay, I have no idea about threads itself, so I have no idea what scope thread would be. Ownership for raw file, descriptors or handles, constant mutex, read write lock, convar, initialization. I don't know what these are. Turbofish for generics, no idea. Non-lexical, okay. I guess the interesting part is like I don't know a lot of these, but it's interesting to look at things like say network related stuff like IPv6 address or things there, which I have an idea of like, and then binary heap, OS string, uh, context. Okay. There are other changes. Check out what changed in Rust, Cargo, and Clippy. What is Clippy? Clippy, bunch of lints to catch. Okay. So Clippy is basically a bunch of lints to catch common mistakes and improve your Rust code. Cool. So Clippy, Clippy lens documentation. So I think for Rust 163 there'll be one. Uh, nice. Warning, allow, deny. Nice. Interesting. This is kind of like your Sonar Cube rules that you have. Let me try to show that once. One moment. Sonar rules, Java, whatever. Mm, yep, got it. So rules.sonarsource.com, and you can see all the rules for different languages and whatnot. So is it there for us? Nope. There is one for Java. So if you click on Java, you'll notice that There are different kinds of rules, some 648 rules. These are static code analysis rules. I think you could call this something similar. I don't know. Is there anything for security? Nope. Restriction, nursery, and whatnot. Okay. So I click on this. What does it say? Checks for empty lines after outer attributes and whatnot. Is there unused variables? No. Interesting. Can I go up and search? Unused, unused unit, unused. Okay. Lint groups, lint levels, all lint groups deprecated. Interesting. Cool. It's nice that they have this whole website to actually do the whole thing. And I love this whole thing. Anyways, but I'm gonna go ahead and like check this out later because this is becoming a bit of a rabbit hole. So yeah, I mean, I'm getting the latest version and we already have it. And cool. So I think we'll be using the latest version from now on. And let's move on to the next exercise. After primitive type 6, we'll have another exercise, I think. Wait, let's just wait for this to complete. 3, 4, 5, 6. Yep. So this is good. I'm not done. Remove that. And then so you have vectors, I guess. It's vex. I'm guessing it's vectors. Yep. So your task is to create a vector, I guess, which holds the exact same elements as in the array A. Make me compile and pass the test, execute this hint and whatnot. The test is this, it says test array and with similarity. Okay. So this is a tuple. Array and vec is a function which returns a tuple, okay, which returns a tuple of integer 32-bit, and this is like a signed integer 32-bit, 4 elements. This is a vector integer 32-bit again signed, and it says something called global. I don't know what that is. And it checks if the first to last element, like 0 to the length of the vectors, right? So declare your vector here with the macro for vectors, and then you syntax is expected semicolon. Okay. So expected semicolon found this. Okay. So no, I think it's expecting semicolon because it thinks it's after this equal to this is the value. So no, that's wrong. Cool. Expected tuple found. Yeah, nothing is returned basically. Cool. So now declare your vectors here. So how do you declare vectors? I don't know. So cannot find value v, mismatch types. Okay. I'm just gonna go ahead and like check out the Rust book to see how I can declare vectors. Vector. Okay, com storing list of values with vectors. Cool. So the first collection we'll look at, its collection type we'll look at is so common collections. Let's see what this is. Rust standard library includes a number of very useful data structures. Okay, called collections. Okay. Okay, all of them are called collections. Number of very useful, like all the data structures are collections. Okay. Most other data types represent one specific value. Okay, but collections contain multiple values. I mean, it can be a list. It can be okay. This is called it. This is similar to this Java collections. I always think of collection like some array stuff and all that. Anyways, so unlike the built-in array and tuple types, the data these collections point to is stored in the heap. Okay, okay. So array is still in stack. Okay, tuple is in stack. I can do that. So which means the amount of data does not need to be known at compile time, and it can grow or shrink as the program runs. Each kind of collection has different capabilities and costs. And choosing an appropriate one for your current situation is a skill you'll develop over time. In this chapter, we'll discuss 3 collections that are used very often in Rust programs: a vector, a string, a hash map. Interesting. Store a variable number of values next to each other. There's a collection of characters. I mentioned the string type previously, but in this chapter, we'll talk about it in depth. Allows you to associate a value like map key value. So associate a value with a particular key, its particular implementation of the more general data structure called a map. To learn more about other kinds of collections provided by the standard library, see documentation. We'll discuss how to create and update strings and hash maps as well as what makes each special. Okay, cool. So storing lists of values with vectors, the first collection type we'll look at is vector, also known as vector T, also known as vector. Vector allows you to store more than one value in a single data structure. It puts all the values. Okay, lost myself over there. Allows you to store more than one value, of course, in a single data structure. Makes sense, like a single unit. Puts all the values next to each other in memory in the heap. Vectors can only store values of the same type. Makes sense. It's homogeneous, not heterogeneous. They're useful when you have a list of items such as lines of text in a file or the price of items in a shopping cart. Okay. To create a new empty vector, we call the new. Okay, so you just have to say new. So can I do that? I don't know. Let's see. Creating a new empty vector to hold values of type integer 32-bit. Okay. Note that we added a type annotation here because we aren't inserting any values into this vector. Rust doesn't know what kind of elements we intend to store. This is an important point. If someone's at the door, one moment. Okay, so I'm back. So where were we? So because we aren't inserting any values in this vector, Rust doesn't know what kind of elements we intend to store. This is an important point. Vectors are implemented using generics. We'll cover how to use generics with your own types, as in like user-defined types, like I think struct. In chapter 10, for now, know that vector T type provided by the standard library can hold any type. Okay. When we create a vector to hold a specific type, we can specify the type within angle brackets in listing 8.1. Okay. We have told us that the in will hold elements of the type this. We put it here. I think we can put it on the right too. I'm not sure. Let's see. So let's just say vec and then new and then this. Can I do that? So 32. It will fail though because 10, 20, 30, 40 will not be there. So left is this, right is this. Okay. So how does it know it's integer 32 bit, like as in unsigned integer 32 bit? Like by default, that's the thing, right? Is it? Or can I say F32? It becomes Boolean. Wow. Okay. Interesting. Here is macro and use colon this instead of this specify lifetime type or const arguments. Okay. I should put again two colons here and then it will become again integer 32-bit. Weird. Expected 0 generic arguments. Okay. Defined here with 0 generic parameters. Okay. I'm not sure how it got its type though. I mean, how did it get its like integer 32-bit over here? I'm just wondering about that. Oh, that's because we are okay. That's because we are actually sending back v, like returning back v, and here we mentioned v is like integer, unsigned integer 32-bit, right? So this should hover, should we? I mean, sorry, signed, not unsigned. Signed integer 32-bit. If I remove this, should be a problem. Unknown. Okay. Expected at least one generic argument. Right. Yep. Cool. So yeah, I mean, we should be this. If not, there's going to be a problem. Can I actually put something else also here? Say something like u, and see how that works. It's unknown here, so declare. Consider giving u an explicit type. As a type for the type parameter t is specified. Can I do colon and then F32 or something? Does it become F32? No, doesn't. 0 generic arguments. Okay, so I think in new does not pick up generic arguments, so we just have to do colon and like just do this and F32 if I want some say floating point 32-bit. Cool. So this is an unused thing, so I'll leave it at that. I'll get rid of this. So this we didn't have to give because we have declared this thing here and we are returning v, so it's automatically that. With that, more often you'll create a vector array with initial values and Rust will infer the type of value you want. Okay, makes sense because here you never give the value, so you can't specify what is the type, and new doesn't take that type as we notice. I have no idea how to call that, however, you're going to learn that. But on the left, you can provide, of course, the type annotation, and that should just work. You want to store, so if you provide the value, it will just infer and understand. Of course, it has to be homogeneous. If it's heterogeneous, there's a problem. So only same type, homogeneous type. So in for the type of value you want to store, so you rarely need to do this type annotation. Conveniently provides the vec, you know, exclamation macro, vec bang macro, which will create a new vector that holds values. You give it, okay. Listing creates a new vector that holds, okay, cool. So we have a macro that we can use because we are given, signed integer 32-bit, either the values or else can infer that this is this. Is it necessary? Next, we look at how to modify it. Cool. So let's do that. Oops. We have a macro we can use. So I'm just going to go ahead and like use that. 10, 20, 30, 40, and the semicolon. And let's see if the test passes. Yep, it passes. Awesome. Cool. So can I do print and then print say v dot or v of 0? Oops, I should provide one formatting specifier. Okay, this has to be a statement. Okay, I can't see the thing being printed. Maybe I should, there's a assert, and then like, maybe I should run this. The test is running. Does it print? Nope. It just checks if the test is run. Anyways, cool. So yeah, I mean, how to access the vector, we'll have to look at that. So updating a vector or modifying a vector and then add elements to it, you can just do push, I guess, here. Can you do pop? I don't know. Oh, you have to do first of all mutate, then only you can do all of that, I think. So v dot concat pop, interesting, removes the last element from the vector and returns it, or none if it is empty. And like if you like to pop the first element, consider using pop front. Okay, interesting. There's no pop front, interestingly. And then there's a push. Cool. So this happens to the back of the collection. Cool. So push, 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 try values as with any variable. Okay, so if you want to be able to change this value, you need to make it mutable, of course. So yep, mute using the mute keyword as discussed in chapter 3. Oh yeah. Just from this data, from the data, so we don't need the, oh, interesting. Like here, it didn't know the value, but since you put the values here, later, it infers that v has integers that are bit. Like, that's awesome, right? It infers later, it understands later. Reading elements of vectors. So you have to say, ampersand, like, you have to borrow or like reference, and then v of 2, two ways to reference the values for indexing or using the get method. Okay, so you can also do dot get. We've annotated the types of values that are returned from these functions for extra clarity. Okay, but you don't need it. Like, Rust can infer the type, but extra clarity. So both methods of accessing a value in a vector with indexing, syntax, and the get method. Okay. So this is the indexing 0, 1, 2. So you'll have 3, third element, and option. Interesting. So get, yeah, it makes sense. Like you could give some index that's like not existent. I guess in this, is it possible, like if you give 100, is it possible to get like a issue or an error, compile error? I don't know. Because this is like, this can keep growing and decreasing in size. Will you get null? None? I don't know. But here it makes sense. It's an option. So note a few details here. We are using index to get the third element. Same thing here. Match third, sum third if it's none. There is no third element. Third element is this. Okay. because vectors are indexed by number starting with 0. Using use as a reference to the element and index. Okay. And we get an option that we can use with match. Okay. Reason Rust provides these two ways to reference an element is so that you can choose how the program behaves when you try to use an index outside the range of existing elements. As an example, let's see what happens when you have a vector of 5 elements and then you have, okay, so what happens? It is able to run it, is it? Oh, this code panics. Oops. So unused variable does not exist. Yeah, that's fine. Warning. Okay, that's all warnings, huh? Right. Interesting. Oh, yeah, here. So these are just warnings. So thread main panicked at index out of 1. So basically, the len is 5, but the index is 100. So it just panics. So when we run this code, the first will cause the program to panic because it references a non-existent element. Yep. And this method is best used when you want to, your program to crash if there's an attempt to access an element past the end of the vector. When the get method is passed at an index that is outside the vector, it returns none without panicking. You'd use this method if accessing an element beyond the range may happen occasionally under normal circumstances. Your code will then have logic to handle having either some or none, as discussed in chapter 6. Okay, this is in chapter 8. So we have to learn what is none. Index could be coming from a person entering a number. If they accidentally enter a number that's too large and the program gets a none, to tell the user how many items there are in the items are there in the current vector and give them another chance to enter valid value. That would be more user-friendly than crashing the code due to your typo. When the program has a valid reference, the borrow character enforces the ownership and borrowing rules. Okay. To ensure this reference and any other references to the contents of the vector remain valid, we call the rule that states you can't have mutable and immutable references. Yep. Basically, reader writer problem. Yep. You can have multiple readers. Yep. But you can't have reader and writer. And you can't have multiple readers. Yep. The rule applies in the string 86 where we hold an immutable reference to the first element, try to add an element to the end. Okay. So first element and okay, so interesting. So we have a immutable reference, so for read reference, and then we have a write reference, immutable reference, and we write to it. After mutable reference, we can't get this, I think, because anyone can mutate in between and this can keep changing or whatever. So if you also try to refer to that element later in the function. Okay, so you say first and you try to read it. Basically, this is gonna say compiling this code will result in compiling collections cannot borrow v as mutable reference because it is also borrowed as immutable reference in the later line, and then it is used here, right? So you are mutating it in between. So, like, this can be any index, but you're mutating it. I mean, you are mutating it here, and you have an immutable reference here. And that immutable reference is used elsewhere. So, I mean, after the mutations and whatnot. So you can't do both of that. Might look like it should work. Why should a reference to like the last element, right? I mean, you are referring only to the first element and you're pushing to the last, right? Reference to the first element care about changes at the end of the vector. This error is due to the way vectors work because vectors put the values next to each other in memory. Adding a new element onto the end of the vector might require allocating new memory and copying the old elements to the new space. Element onto the end of the vector. Okay. So sometimes you will, if you require, might require like more space. Let's say you didn't have enough memory. So, and copying the old elements into the new space, if there is enough room to put all the elements next to each other, as vector is currently stored. In that case, the reference to the first element would be pointing to deallocated memory. Okay. So this is like a reference, right? This is borrowing. So if you push and there is not enough, say, memory, this is pointing to some, say, A, B, C, D, whatever, A, B, C, D, E, some 5 memory addresses. But now you move on to like say F, G, H, I, J, K, L, M, so on, and you would have, then A will become invalid, like the memory will become invalid. The boring rules prevent programs from ending up with that situation. Interesting. Iterating for IN. Cool. I guess I'll check these out later, but this program is pretty much cool and done. So I'm just gonna go ahead and like move on with the next exercise and also read this on the side. And I'll see you in the next one. Bye-bye.